Thanks, Toby. Next up, we have McKenzie Peters from the North Carolina State Climate Office with a perspective on leveraging long-term observations for monitoring and communication.
Yes, hello. So again, my name is McKenzie Peters, and I'm a researcher at the North Carolina State Climate Office. So before I kick this off, I'd like to quickly acknowledge my co-authors on this, Sean Heuser and Corey Davis. Okay, so I'd like to get the story started here with the U.S. Drought Monitor, which was touched on a little bit earlier today. But in case you're not as familiar with what it is, it's a weekly map of the U.S. showing where drought is occurring and to what severity it's occurring at. The authors for the U.S. Drought Monitor include people from the National Drought Mitigation Center, the USDA, and NOAA, and they use a convergence of evidence approach. They use a convergence of evidence approach to assess where drought is occurring in the U.S. They look at physical indicators as well as drought impacts, but they also take into consideration input from the state level. So in North Carolina, we have a Drought Management Advisory Council, and they release this map weekly showing where drought is occurring within North Carolina. And they look at different physical indicators such as stream flow, reservoir levels, precipitation, and temperature data, but they also take into consideration farmers' accounts of what they're seeing out in their fields. So back in the fall, I had an opportunity to attend one of these meetings, and afterwards, I had a chat with my colleague Corey, and we realized that soil moisture was excluded from the conversation, which I thought was strange, given that soil moisture is pretty well correlated with drought. And we realized that this is because it's hard to interpret without knowing anything about the soil types at our stations or the typical values that they are associated with. So here we have a map of North Carolina, and this shows soil moisture conditions for May 28th at the 20 centimeter below ground level. And as a quick crash course on North Carolina geography, the western region is relatively mountainous, so here we have a lot of gravelly soils. And then the central Piedmont region is more clay-based, so here we have some red clay shown at our New London station. And lastly, our eastern portion is our Sandhills region. And as you probably guessed it, we have a lot more sandy soils in this region. So all this heterogeneity across North Carolina basically renders this color bar to be meaningless, because different soil types are not going to have the same soil moisture values. So if we take into consideration two of our stations, so Jockey's Ridge out here on the East Coast, and then we have Plymouth, both are close together both are relatively close together geographically. So they experience pretty much the same precipitation, but they have such drastic values. And that's because our Jockey's Ridge station, so the more eastern one, is pure sand, while our Plymouth station is loam. And our sandy stations never really get that saturated when compared to the loam station. So this prompted us to want to build a web tool to communicate soil moisture in a way that's meaningful, especially for the folks who are trying to assess where drought's occurring in North Carolina. And the way that we wanted to do this was to present soil moisture observations as historical percentiles to show where it's perhaps wetter or drier compared to normal. And for this, you need a relatively lengthy soil moisture data set, and luckily we have that in-house. So the State Climate Office is home to our Environmental and Climate Observing Network, also known as the EcoNet. And this is a network of 45 10-meter tall towers across 35 counties, measuring various meteorological and environmental parameters at a temporal resolution of 1 minute. This includes soil moisture, which we measure at 20 centimeters below ground level. 20 centimeters below ground level. And we use the theta probe, and we also express this as a volumetric water content. So last thing I'll say here is that the EcoNet was established as an agricultural monitoring network. And because of that, we have a relatively lengthy period of soil moisture observations, just because this is something that farmers were particularly interested in early on at the inception of our network. So because of that, this kind of lays the groundwork for a climatological approach. And we'll go into a little bit of the methodology here, but nothing too into the nitty-gritty. So again, we want to focus on stations with relatively long periods of record. There we go. And that means we want to look at stations that have more than 20 years worth of data. So of our 45 stations, this then brings it down to 25, which is still a relatively good sample size to include in our analysis. Then for each station, we removed any values greater than 0.6 for quality control reasons. And then we also removed any values less than this permanent wilting point of each soil type. And quickly, the permanent wilting point is the threshold at which soil holds on to water so strongly that the roots can no longer extract it. And this varies by soil type, and therefore it varies by stations. You can see our stations here color-coded by their soil types. Then we wanted to group this data by month because we determined that monthly climatology is going to be the most applicable and easiest to understand for the folks in DMAC. And then we calculated climatological normals based on these percentile ranges. So the dry percentile ranges are taken directly from the US Drought Monitor, because these are the historical percentiles that they look at when looking for drought indications. And then we decided it was also useful to show when things are wetter than normal. Then we took the inverse of that over the 50th percentile, and that's what we've got here. And then again, we wanted monthly percentile ranges because this is what we thought would be the most useful. And when we do that, we get something that looks like this. So this is a 12-month time series that we show on our web tool, but I want to go over a few quick features before I show the entire tool. So here we have a 12-month time series of our daily average data, and this is exemplified by the black solid line. We also have our monthly medians, which are represented by the black dots. And then the background, you can see the shading of the percentile ranges according to the color scheme that I presented on the previous slide. So the benefit of plotting the time series like this is that we can see when periods are considered to be more wet or dry compared to climatological normals. And if we look at an example, a value of 0.27 isn't going to mean a whole lot on its own. But if you look at the month of October, we can see that 0.27 is actually considered moderately dry at this station. Another useful feature about this time series is we can see the impact of precipitation or perhaps the lack thereof. So this time series is from Mills River, which is a station right outside of Asheville, North Carolina. And we can see the increase in soil moisture values as a response to Hurricane Helene. The other interesting thing is we can see the period of drying out afterwards because there was so little precipitation that occurred throughout that region. So the last main feature I want to show on this is the soil textural group and class information. So this is important because the soil textural class dictates the lower limit of what's considered exceptionally dry, and that was used in the filtering that I explained earlier. The other thing is we can start using the soil textural group to start explaining some of the differences that we might see across our stations. So while I don't have any other stations up here, this station has a medium textural group, which means it's not going to dry out as fast as perhaps a more coarse soil, but it also doesn't stay as saturated as a more fine soil. So on top of seeing how the soil moisture changes with time, we also thought it was going to be, we also thought it was important to show how changes spatially with geography. So here we have a map of our 25 stations, and in the center we have our daily average soil moisture values. And then the colors correspond to the percentile ranges that those stations are currently in given that specific daily average value. The other thing we have here is our marker shapes, which are indicative of the soil textural groups at each station. So we have coarse soils represented by circles, and this is going to be more along the lines of sandy soil. And then we have triangles representing medium soils, so this is going to be more like our silt. And then finally, we have squares representing our fine soils, and this is going to be something along the lines of clay. So the benefit to having a plot like this is that we can start doing some cross comparisons against stations. So if we take these two stations, for example, they both have fine soils and they both measured a value of 0.31, but they're drastically different. And the northern station has a severely wet categorization, while the bottom one is considered to be normal. And the difference for this is because the top station has a sandy clay loam soil, whereas the bottom one is just sandy clay. So now having gone over the two hallmark figures of our web tool, this is kind of what we're looking at now. So upon loading, the map will populate with the most recent daily observation. And because I put this together on May 28th, this is showing for May 27th. And then we also have our time series, which automatically loads for Lake Wheeler, which is the station closest to the state climate office. So then if you want to change the station, you can easily click the map and it will automatically generate the new station plot. Or you can use the drop-down menu if you don't want to try and click around and try and find the station you're looking for. The other thing you might have noticed already is that we have tooltips. Oh shoot, okay. We have tooltips and you can see the different values for each of these. You can see the different soil moisture values and then the percentile ranges as well. And because I'm low on time, we'll probably just skip through the rest of this. And this just shows everything that's in the web tool. I'll have a QR code at the end if you want to see more. So some of the other interesting things here is that beyond drought monitoring, we can use this for geological research. So we can use this to assess where regions might be more susceptible to landslides, because if we have more moist soils, there's going to be an increased landslide risk. We can also use this for fire weather monitoring, since dry regions are going to be more conducive to wildfire spread. And lastly, we can use this for validation of agricultural impact reports, or even validation of model data sets like the NASA SPOR LIS data set. I also have a few research questions that I would like to tackle using this tool and the data set that I've created. And the first one would be a comparison between our EcoNet soil moisture data and remote sensing observations, just to see if they're measuring the same thing. And then if it rains, do they increase at the same rate? Or if it dries out, do they decrease at the same rate? Another thing that I'm interested in looking at is how do these soil moisture values translate to drought classification? So the question that we would pose here is, what is the probability of an exceptional drought given a certain soil moisture value? So again, as promised, here's the QR code. And all the visualizations I showed in this presentation were from the development version, but I am happy to announce that this tool actually went live last Friday. So this URL and the QR code will bring you to the State Climate Office website with the live tool. So please let me know if you have any questions or any suggestions for improvement. Thank you.
Thank you for that. I like that scale, the color scaling down from the drought severity. What can you just explain, maybe you said something, but I guess, but over what time period those data collected, come up with that, and then wondering if you're seeing temporal changes just over, say, the scales.
Right, so the data that we started using here was going back to 2001. So we're using 2001 up to present day observations to create this climatology. I personally have not looked through all the years to see if there's any trends in the data yet, but that's definitely something that we're interested in looking at going forward.
Thank you very much. Next up, we have our concern.